Hi, I'm Jeff Hollingsworth, and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving our over 100,000 computing professionals and students who are ACM members. I'm a professor of computer science at the University of Maryland College Park. My research interests include dynamic instrumentation and auto-tuning for high-performance computing. I'm editor-in-chief of the journal Parallel Computing and vice chair of ACM's Special Interest Group on High-Performance Computing, SIG-HPC. ACM offers educational and professional development resources to bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing computing world with a wide range of ACM learning resources available at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving innovation that sustain competitiveness in a global environment. Among its services, ACM provides timely information published by ACM, including Communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, and international conferences that draw leading experts on a broad spectrum of computing topics, as well as support for education and research, including curriculum development, teacher training, the ACM Turing and ACM InfoSys Foundation Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances us in the digital age. Before we get started, I'd like to mention a few housekeeping items on the slide in front of you. In the top right corner of the slide area on your screen, there is a button that will allow you to enlarge the slides. You may also enlarge the slides at any time by dragging the corner of the slide window. The slides will advance automatically throughout the event. During this presentation, you can minimize the slide area, Q&A, and bio screens using the buttons on the bottom panel. You can also use a number of widgets also found on the bottom panel, including ones for Facebook, Twitter, Wikipedia, and a resource list where you can get a copy of the slides. If you should experience any technical problems during the web presentation, please refresh your screen by pressing F5 on Windows or Command-R on a Mac. If you're using a mobile device, refresh your browser. If all else fails, relaunch your web browser and try again. Also, you can visit the webcast help guide by clicking Help below the slide window. To control your volume, just use the normal master volume on your computer. Importantly, at the end of the presentation, we will have some time for questions and answers. If you think of a question during the presentation, please type it into the Q&A box and click Submit on the button. You don't need to wait until the presentation ends to submit your questions. You may also use the Q&A box and the survey at the end to suggest topics for future webinars. At the end of the presentation, you will see a survey URL on the final slide. Please take a moment to fill it out and give us important feedback about our webinars. This session is being recorded and will be archived. You will receive an automatic email notification when it's available, or you can check back at learning.acm.org in a few days for updates. You can also use Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions during the webinar or afterwards. The hashtag is ACMWebinarGPU. We'll be watching for your tweets, and if you send questions that way, we'll also include them in the Q&A at the end. Today's presentation is Achieve Massively Parallel Acceleration with GPUs by Mark Ebersole. Mark is GPU programming educator at NVIDIA, where he teaches developers the benefits of GPU computing using the CUDA parallel computing platform and programming model, and the benefits of GPU computing. With more than 10 years of experience as a systems programmer, Mark has spent much of his time at NVIDIA as a GPU systems diagnostics programmer, in which he developed a tool to test, debug, validate, and verify GPUs from pre-emulation through bring-up and into production. Before joining NVIDIA, he worked at IBM developing Linux drivers for the IBM i-Series server. Mark, we look forward to your presentation today.
All right, thank you, Jeff. Can you hear me? Just to make sure my audio is on.
I can hear you.
Excellent, thank you. All right, welcome everybody. Thanks for listening in. As Jeff said, my name is Mark Ebersole, the CUDA educator at NVIDIA. I'm going to start with just a real brief recap of what NVIDIA is, if you haven't heard of it before. It's a company founded in 1993 by three guys in their apartment. Jensen Huang, our CEO, has been our one and only CEO. In 1999, NVIDIA invented the modern GPU. Around that time, there were about 30 companies looking into the hardware graphics world. NVIDIA is the last remaining of those 30 companies, with ATI having been bought by AMD. We get the question a lot, why do I care about GPUs for my supercomputer or for doing scientific programming? And it really has been the gaming world, the graphics world, that led to a general purpose, really powerful, massively parallel accelerator, which I'm going to talk about today. So the 3 points I'm going to go over to help you take away from this presentation is, first, what is accelerated computing? What do we mean by that? It goes by many different names, but what is accelerated computing? The why and how to actually program GPUs, why you care about doing accelerated computing on a GPU, how you can actually get started. And then finally, I'm going to end with a number of resources if you are interested, where you can go to learn more, how you can actually get started, what you need to download. And so these are the sections you're interested in. And these slides will be available for download later, so you can you don't have to worry about scribbling down links. You can always go and get them later. So these are my 3 points, and let's get started. So the first important one, why accelerated computing, and it really starts with Moore's Law. And for Moore's Law, it's the graph of the last 40 years or so of the number of transistors in a system over time. And I always get interesting responses when I ask what is Moore's Law at various talks, and I usually get the response of it's the power of a computer is going to double every 18 months to 2 years, or the speed of a computer. And Moore's Law is actually about just the transistors. And my favorite quote of Moore is that if Al Gore invented the internet, I invented the exponential, because people tend to attribute Moore's Law to anything of exponential growth in the computer world. But his law was really just about the transistors. The number of transistors on a chip will double every 18 months to 2 years. We've done a great job of keeping up with that law. We don't see it slowing down, at least in the next decade. But then that brings us to this graph, which is just simply clock speeds in various processors over time. And you can see for the first 40, 30 years, we kept up with the number of transistors. As transistors doubled, the clock speeds doubled. But in the last decade or so, clock speeds have really just done this hockey stick. They've hit this brick wall, or they just aren't getting any faster. And so what makes up this brick wall? Why is this happening? Why aren't we see our processors just getting faster as they did for so long? And it's really broken down into 3 areas. There's the power wall. As you drive, as these transistors get smaller and smaller, and we're packing more of them into a smaller area, it's just become unscalable to be able to dissipate all that heat and to keep cranking clocks. So we can no longer just wait for the next processor to come out for our single-threaded applications to go faster. So we just can't drive enough power through it. There's the memory wall, which hits all processors. Processors can't do anything. They can't do all the processing without data, and it's really hard to get the data off chip, on chip, fast enough for our processors to handle it. Modern CPUs deal with 3 levels of very large caches, getting bigger and bigger, using more of these transistors we have available for larger caches. But it's a problem that affects all processors. And then finally is the instruction-level parallelism wall. Instruction-level parallelism is a really cool and complicated set of tools that are built into the hardware to help us software guys make our code go faster. These are tricks that are trying to actually predict the future, trying to figure out what path your code is going to take and execute that code ahead of time to try to speed it up, running code in parallel. And it's lots of really cool tricks, but the problem with this is it's becoming a superlinear increase in complexity to get a linear increase in speed, and you can't sustain that. So we're getting to the point where we're spending more and more transistors to try to make our single-thread applications go faster than we have the transistors to actually do the work. So these are some of the 3 main reasons why we just aren't seeing processors get going faster, and why processors today are all now going wider. They're going parallel. The world isn't getting faster anymore. It's going wider. And so the answer to this is really what we call heterogeneous computing, or accelerated computing, what you want to call it. It's combining the best processor for the job, combining the CPU and some sort of accelerator, and using the right processor for the job. And this is really what we're going to need to do on our scale, or on our path to exascale, kind of the new space race. Which country is going to get to an exaflop machine by 2018, 2020 time? And it's this heterogeneous computing, using the right processor for the job. And the idea is really simple. It's keeping your sequential code, your heavyweight threads on the CPU doing what it does best, making a few threads run really, really fast, or for stuff like file I/O or running the operating system, or for algorithms that just don't scale to many thousands of processors just because of communication issues. And then you take your compute-intensive functions, your highly parallel functions, and you move them to your accelerator. Accelerators don't really care as much about a single thread speed. They're more concerned about the throughput, trying to get billions of threads to run through in a second, as opposed to a few heavyweight threads going as fast as they can. And this is what the talk today is going to focus on. How do you actually get your code over to the accelerator? Today, there are basically three major accelerators from NVIDIA, AMD, using their ATI GPUs, and then Intel is now in the arena with their Xeon 5s or their Mic processors. The form factors I'm showing here aren't the only ones. These are discrete accelerators that actually plug into a PCI Express slot. There's accelerators that exist on die with the CPUs, and there's, you could have an accelerator in the cloud where you're actually having to go over the internet to access the processing power. So this isn't the only form factor. There are many out there. And there's also FPGAs, which are basically dedicated machines for doing a specific algorithm, like Bitcoin mining. If you put your one specific algorithm in this machine, it's going to be able to go faster than these general purpose processors. But these are the three major ones out there. So NVIDIA GPUs, you can actually find them in a variety of form factors. You should probably actually switch the car on the right with the Titan supercomputer. It's not sized to scale, but you'll find fully programmable GPUs in all these systems, from the traditional desktop and laptop up into supercomputers. You actually won't find a supercomputer being built today that doesn't have some sort of accelerator providing most of the computational power, because they're also very power efficient. The top 10 greenest supercomputers are now powered by NVIDIA accelerators, because it's all about power efficiency. So now with our launch of our Tegra K1 chip, which we announced last year, which has the fully programmable GPU in it, and actually the same class of GPU you can find in the Titan supercomputer, just at a much smaller scale, in your phones, and Audi and a number of other car manufacturers have announced putting these processors in their cars, not just to generate pretty pixels, but also to do computation. Look ahead to do image processing on the road in front of you to detect bicyclists or pedestrians crossing in front of you, driver assistance type of system. And so you find these programmable GPUs everywhere in today's world. Just some examples of where GPU has been used, some medical examples. So CT scans, this is where you go in to look inside the body, usually using some sort of radiation to get a 3D picture of what's going on inside. So unfortunately, to get these images, if you're not using MRI, again, you are being exposed to radiation. So one of the goals of these projects is to cut down on the amount of images needed to be taken to cut down on the radiation you're exposed to. And so researchers have found if you can take just much fewer pictures, but at its very specific angles, you can get a very noisy image, but since you know how the pictures were taken, you can denoise them using an algorithm. So you're just running through all this massive data through a processor to generate a useful image. And before moving to an accelerator in a massively parallel processors, it would take sometimes days to do a single image, and this is just not clinically practical. You have all these patients coming in, you don't have time to do this. But by moving to GPUs and accelerators, they were able to cut the time down to almost real time. Maybe just a few minutes later, that they would actually have a useful image while cutting the radiation down drastically that they're exposing their patients to. So this is one of the very early adopters of GPUs and accelerators. The next up, another medical example. Normally this is a video slide, but it doesn't come over well here, so I'm just going to use some static images. So what you see on the left is it would be a beating heart, an actual moving heart with this grid superimposed on the image. And instead of the surgeon actually operating on this beating heart, traditionally they would stop the heart, which is very dangerous, so they'd only tend to do it in a life or death situation. What the surgeon would actually operate on is the image on the right, which is a virtually still image of that grid. And so the surgeon's actually using a robot to do this operation. And so they're working on the still image on the right to do all their operations, the cuts and stitches and stents. But the heart remains beating, and they actually have this machine sitting over the patient with these 6 arms, and it's motion compensating with the beating of the heart. So the arms are actually moving as the heart does in real time, and translating the movement, the motions that the surgeon's doing on the virtually still image over to the actual beating heart. So you're getting the best of both worlds. The surgeon gets to work on the still image while the patient's heart, you don't have to stop the beating heart. And this is, again, only really possible with the right processor. To do this type of computation real time, you would need a supercomputer hooked up to the operating room, and that's just not feasible, especially at scale. And then you have to worry about failures and rollovers, where if you move to heterogeneous computing with an accelerator, you can have 3 of these systems, right next to the operating system room, if not in the room, to handle failures and rollovers, and it can handle that amount of power because it's what it does best. So there's just a few examples. I'll go over a few more here at the end. There's many, many of them out there. You can go through and look through them on our resources page if you're interested in learning more. So now, how do you actually use the GPU to do this massive acceleration? We always get a lot of concern, why am I using this thing which draws really cool pixels from my Call of Duty game to actually do scientific computing? Do I have to learn graphics APIs? What is it? How do I actually use it? So for NVIDIA, if you've done anything with this GPU computing, you've probably heard of CUDA, especially related to NVIDIA. And so what is CUDA? Is it a programming language? Is it a compiler? This is actually what CUDA started out as. It was a CUDA-C compiler. If you do a search for Google, or if you do like a Google or Internet search for CUDA, or on Twitter, you get a lot of interesting results. There's the classic CUDA car, which a little anecdote. This is where the CUDA name actually came from. Was this car? There's a CUDA beer out there. There's a wine. There's coffee. CUDA is also shorthand for could have. So if you do a Twitter search for CUDA, you're going to get lots of very interesting results. But CUDA is really NVIDIA's parallel computing platform, the platform from getting access to all this massively parallel power you have available on the GPU. It's the programming approaches, which I'm going to go into some more detail in the rest of this talk. It's the development of art around it. It's the open compiler tool chain we have available around LLVM. And it's specific hardware capabilities we're putting into our GPUs for computation. GPUs are traditionally made for graphics, but we're also now, given the desire for people to use these for general purpose computation, we're putting in hardware capabilities specific to that, such as dynamic parallelism, where a single thread among billions can launch a whole new grid of work instead of having to wait for the CPU to relaunch the work, capabilities like that. So CUDA is really our parallel computing platform. And what has this done? So combining our general purpose GPUs with CUDA, in 2008, about a year after our first CUDA-capable GPU came out, we had 100 million CUDA-capable GPUs in the world, 150,000 downloads. It was a little bit of uptake, but not a lot. It was still really new and kind of people considered a fad at that point. But now you fast forward to 2014, we have actually over 500 million CUDA-capable GPUs now. I need to update the slide. 41,000 supercomputing teraflops. Again, it's the vast majority of supercomputers that use accelerators are now using our GPUs. Universities are now using CUDA to teach parallelism because it's a very simple way to get access to all these thousands of threads to be able to teach massive parallelism, and just many, many papers being written on this. So it's really taken off as a technology. It's no longer a fad. It's just become a de facto way to get accelerated computing. Now, how do you actually accelerate your applications? We say 3 ways. I like to say 3+ ways. I'm gonna go into those. The first is just somebody's done the work for you. They've accelerated an app that you need. So in this case, you would just go and find an application that already has GPU acceleration. If you have access to an NVIDIA GPU, you put in your data, and it just runs much faster. Again, it's somebody's already done the work for you. This is the easiest way to get started if you have one of these apps. You can find our list. We have, I think, it's up to 275 now and growing. You can go to NVIDIA.com/apps catalog and look through, big names like Amber for molecular dynamics, to lots of different graphics processing APIs, doing real-time rendering, those types of things. So lots of apps available. So that's the first place you should go look. Just some quick perf numbers. So, comparing a very powerful CPU trying to do something it's really not made to do, force parallelism to a massively parallel accelerator. You really get great speed-ups just by adding this extra piece of hardware into your system. So if there's not an application out there, you're actually looking to develop your own code, the next step that you should look at is libraries, what we call drop-in acceleration. This is where somebody's gone and done all the hard work of implementing an algorithm, and you just call an API. We've been doing this in computer science since near the beginning. Same things here. There are many, many accelerated libraries out there. I do like to tell people here, don't reinvent the wheel, even though it's a cool new technology. Unless you're doing something for just educational purposes, don't rewrite matrix multiply. That's a solved problem on an accelerator. Go out and find a library that does it and just re-implement it. We see this all the time, which is why I bring it up. People give this really complicated algorithm, and as you break it down, you realize they're just doing, like a matrix multiply or a fast Fourier transform or something that's a solved problem. There are libraries out there that'll make it go as fast as possible. So please look through the list if you're going to start getting interested in accelerated computing or GPU computing. NVIDIA maintains a number of what we call building block libraries. They're the ones highlighted in green here. Stuff like basic linear algebra or random number generators or sparse matrix operation, performance primitives, any kind of signal processing library, FFTs. We like to build the building blocks and have third-party companies build on top of it, companies such as Magma, MATLAB, other companies that use the basics to build more complex algorithms. So lots of libraries out there. Thrust is a really important one I like to call out if you're going to do any kind of C++ programming and you want to embrace parallelism, which you should. It's very similar to the standard template library or Boost. You're not actually writing any GPU-specific code. You're just using a device vector and then calling a bunch of various functions on it. It's got different backends, so it's portable. It compiles to OpenMP or Intel Thread building blocks, so it's a really great way to quickly get parallelism into your C++ code. If you want to see a list of what we know out there, you can go to this link at our developer site, NVIDIA.com. This will list all the libraries we know of out there, both third-party, open source, ones NVIDIA maintains, all those, and kind of the area they're featured in, so you can go dig down and see what's available. All right, so once you've exhausted the libraries options, you've called everything that's already been done for you in your libraries, really the next easiest step as we kind of go down the scale is using directives. And directives are simply compiler hints to, in Fortran, C, and C++ to the compiler on how to optimize code or how to parallelize code. If you've ever used OpenMP before, this is very similar. In fact, OpenMP has recently, with the 4.0 specification, has added targets for devices such as accelerators. So OpenACC and OpenMP are actually heading in the same direction. The plan all along has been to merge them eventually, but for now they're separate specifications. But again, you're providing hints to your compiler. You're not having to modify the underlying source, which is a great way to keep it portable. So if the compiler understands the hint, it will try to do the work, and if it doesn't, it just ignores them. So it allows you to keep your code very portable. OpenACC, the compilers work across all the major accelerators, even targeting some CPUs as well, and so it's a great option for keeping portable across the hardware. Just an example of SAXPY. So here's single precision A times X plus Y, just a simple for loop. So OpenACC is on the left in C, and then on the right in Fortran. You're just adding these 2 lines in green, or 1 line for C and 2 lines in Fortran in green. And this is telling the compiler, okay, go and compile this to run on the accelerator for me. You're not having to write any of that code yourself. And this is what it would look like in OpenMP, very, very similar to OpenACC. So if you've done OpenMP before, it's virtually the same, just a different directives and clauses you got to use. Right now for OpenACC, there's three of the major compiler vendors, CAPS, Cray, and PGI have compilers out there. The OpenACC 2.0 specification came out last year, and the compilers are just starting to roll out. It's a really great enhancement to the original OpenACC spec. Made it a lot more flexible and a lot more useful in porting your code to the GPU or an accelerator. GCC is also planning on doing an open source version, hopefully targeting late this year or early next year, whereas the three major compiler vendors are for pay-for compiler licenses. The OpenACC and the GCC will be a free one coming out as open source. All right, so that was directive. And then finally, we're going to get into programming languages. So I believe most of you on this call are developers. I'm going to spend a fair amount of time on this one, actually getting in and writing code for your accelerator and specifically your GPU, where this gives you your maximum flexibility. You can do the most amount of stuff, but you also have to spend the most amount of time writing it. And I will say all these can be combined together. You can do libraries, directives, and programming languages all on the same application, and we actually encourage you to do that. Do as much as you can in libraries, as much as you can in directives, and then finally get into programming languages when you either can't get something accelerated or you just want to optimize it as much as you can. There's a number of CUDA-enabled or GPU programming languages out there. C was the first one, but there's C++, Fortran. There's now a CUDA Python where you're directly writing GPU code in Python. It's from a company called Continuum Analytics, where it's not just a wrapper for C. You're actually writing it in Python. There's F#, the R statistical language has support, MATLAB, Mathematical LabVIEW. There's many, many languages out there where you can talk directly to the GPU from within that language. So one of our recent releases of CUDA, CUDA 6, which the release candidate's out now, and the production release is coming out very soon, we really focused on lowering developer effort, trying the amount of time you need to spend porting your code to get the benefits of an accelerator. One of the big features we just announced is called unified memory, where, since we are working with two processors, we have two separate memory spaces. You have your accelerators memory, your GPU memory, and then your system memory, your traditional, CPU memory. And before CUDA-6, you had to manage these yourself as a programmer. You had to worry about allocating data in both places and copying it back and forth. And while definitely doable, it became a hassle, especially for the first effort to get a code ported. Before you can actually get something running, you had to do a lot of memory management just to get it running. So unified memory is really our goal to get rid of that necessary effort at the beginning, where now you just have one memory space from a programmer's perspective you're working with. You have one pointer you're working with. You don't have to worry about copying it. That all happens under the scene. You can still manually go in there and optimize with memory copies and doing it since you know what your data is going to do, but it is now just an optimization. It's not a requirement. So I'm actually going to run through some examples of how you would write a CUDA-C or C++ language, one of our first CUDA-enabled languages. Our goal with CUDA was to make the learning process as simple as possible to get access to these thousands of threads you'll be managing. How do you actually do that? And so we really try to keep it as simple as possible. So we just added a small set of extensions to what you already know, and then just a few APIs that you actually have to call to be able to get the access to the full power of the accelerator. So in this session, it'll help if you know C++, not really necessary. It's not overly complex code. If you've done any kind of programming, you'll be able to pick it up. But I think the biggest thing about the prerequisite is you don't need GPU experience. You don't need parallel programming experience. You don't need graphics experience. We're doing nothing with the graphics API here, no DirectX, no OpenGL. This is all just straight C code with a few small API calls. So just some concepts. I've already hinted at these, so you've probably already picked up on it. When I say host, or the industry says host, we mean the CPU and its memory, the host processor. And then we say device, it's the GPU or the accelerator and its memory. There's those separate memory spaces, but we're merging those now with unified memory. So you'll see, and through our code, we actually don't really have to worry about those memory types anymore. So this is the code we're going to accelerate. We saw it already. SAXPY, we saw it done with OpenACC and OpenMP. Now we're actually going to write it with a CUDA-enabled language. So it's a simple for loop. Goes from 0 to, in this case, I think I have 1 million elements, and it just does this very simple algorithm. So before we begin, a couple concepts we need to know about a CUDA-enabled language. And the parallelism on a GPU is actually broken up into multiple levels. It's, it's not just a simple SIMD thing. It's a very complex layer of different types of parallelism that through CUDA, we make very simple to get access to. And the first concept you need to know is what's called a CUDA block. So we actually run a function on a GPU. It's called the kernel. So you'll hear this concept a lot in parallelism. When you're launching something, you're launching a kernel. And I like to think of each parallel invocation of our function. So we have our SAXPY function. When we run it, it's called a block. Now, I'm a very analogous learner. I like to learn by analogy, so I'm going to use an analogy for you guys. So I like to think of a block as a hamster cage. So just go with me here for a minute. So a block is a hamster cage. And when you launch a kernel on the GPU, it gets an idea of it's called a grid, because you can have multiple grids. So you have many exact duplicate copies of our block, of our function, or what's a hamster cage. Now, because these are all exactly the same, they're copies of each other, we need ways to identify them. So in a CUDA language, there's a read-only variable you get to work with called the block index. And so each one of these cages is going to have a different block index. So they know what part of the data to work on or which function they're supposed to be doing. And you can have different grids running on the GPU at once. For an example, say you were playing a game. You could have one grid being the physics engine that's handling all the physical simulation. Then you have another grid that's actually doing the rendering for you. So you can have multiple grids running on an accelerator at once. So you have different looking hamster cages, different numbers of them, or whatever. So just keep in mind you can have different grids running at once. So our next concept is called a CUDA thread. And now each block is then broken up to threads. These are what actually go through the code and do the work. They're actually doing the processing. If you can see where my analogy is going, I like to think of a thread as a hamster. So these are the guys actually doing all the work for you from within their cages. And just like the grid, a block is made up of identical threads, and they also need a way to identify themselves so they can figure out which piece of data to work on. So they have their thread index, 0, 1, 2, up to however many hamsters we have per cage, -1. And finally, one additional variable we'll need, as we'll see here shortly, is the block dimension. This just simply tells us how many threads we have per block or how many hamsters we have in each cage. So why do we do this? Why do we have threads and blocks? This is really a way for what we found is the easiest way for the software developers and programmers to be able to access all these thousands of parallel cores available on a GPU in a controllable manner. And so threads within a block, or you can think of all the hamsters within a single cage, they can communicate very quickly, what we call share memory. Very easy for them to share data, and they can also synchronize on each other. They can wait for all the other hamsters to finish what they're supposed to be doing before they move on. But threads out in different blocks are unable to do this. So you can think of blocks as very independent units that can be scheduled at any time. And we did this because it would be really hard, if not impossible, in hardware to implement a solution where every thread out of billions of threads can all share and communicate and wait for each other. I mean, you'd have deadlocks, and it was just virtually impossible to do in hardware. So this is why we have blocks. And by also requiring the blocks to be independent, it's very easy to scale. And the whole point of parallelism is just as you add more processors, things just go faster. So by blocks, if you can program on your laptop GPU, get your algorithm working, and then when you move that to your Titan supercomputer with the really powerful GPUs, there are more blocks available. It just goes faster. For my contrived example, if I have GPU X that can do 2 blocks at a time, it takes me 4 time steps. I move to a more powerful GPU that can do 4 blocks at a time. It takes half the time. So this is another benefit of moving to the block structure. How does this tie into a block diagram? This is what we call the architecture version of one of our recent GPUs. This is not what it actually looks like. Don't worry too much about any of the words or anything. I'm just trying to tie in the concept I've given you to the hardware. So when I say a grid, it's talking about the whole GPU. So a grid runs on the GPU. When I say a block, it's tied to what we call an SM, streaming multiprocessor. And so a block runs on one of these things. And you can have multiple blocks running on these at once, but that's where the block ties to. And then finally, the threads or the hamsters, that's all the little green and orange dots you see on the screen. To continue with my analogy, you can think of these as the hamster wheels, all 2,048 of them that you see in this picture. This is where the hamsters actually run to do their work, or where the processors, the threads, execute on to do their work. So there's many thousands of these on a modern GPU. And so this is what the CUDA program is trying to give you controlled access to. All right, so back to our example, our SAXPY example. This is the kernel or the function we're going to accelerate. So this is the serial version on the CPU. And then this is the GPU version, our SAXPY kernel. Nothing overly fancy. We didn't change much. The first thing you'll probably notice is this __ global. And so in a CUDA-enabled language like C, this tells the compiler that this function will be running on the device, on the GPU, and we can call it from the host. So that's all we needed to say. This is now a GPU function. You'll now notice our 3 variables we talked about earlier, the block index. This is the ID of all the different blocks or the hamster cages. We have our block dimension. This is just the number of threads we have per block, or the number of hamsters per cage. And then finally, our thread index, which is the ID of this specific thread that's running this code. So if you look at this algorithm, it's actually, all this is doing is getting I to go from 0 to n-1. So we're essentially replacing the for loop by spreading it across all the processors available on our GPU. And so now the I is indexing into our input and output arrays. You will notice we've had this if statement, if I is less than n, where n is the number of elements we're processing. Just like a for loop or any loop, we don't want to do more work than we have data, or otherwise you start overriding data, which we all know is bad. So this is a check for in a case where our data doesn't perfectly divide into the number of threads we have available. So this is just a check where some of our threads in a block are doing work, but there's some threads that are just hanging out, not doing any work. They don't have anything to do, so we want to make sure they're not overriding memory. So that's what that if statement check is for. So let's just run through just a 30 data element just to see how this works. Obviously, you'd want to move to the accelerator when you have a lot more than 30 data elements to work with, but just to walk through here because it would take a while to do a million. So I arbitrarily decided let's do 3 blocks with 10 threads per block. Or you could say, or we have 3 hamster cages, and each hamster cage has 10 hamsters in them to do our work. So our block dimension is 10. We're now going to say for the first block that has an ID of 0, 0 times 10 is 0, and then we add all our thread indexes. This is how we get I to go from 0 to 9. And then same thing for block index 1. We now have the I going from 10 to 19 and so on to 20 to 29. Where if I had now said let's do 11 threads per block, you can see this last block is going to have 3 extra threads that we don't want doing work, and so that's where that if statement comes into play. I just bring up that if statement because that's one of the first errors we see when new CUDA programmers writing actual CUDA-enabled code is they forget that if statement. And it works for their contrived case, but as soon as they apply real data, they start getting weird errors, and it's usually because they're missing that statement. So that was it. That's all we needed to actually write our CUDA-enabled version of SAXPY. So how do we actually call this code? This used to be a much more complicated slide, but now with unified memory, I can do this on one slide very simply. So I'm going to start with two pieces of code that are exact same on both sides. I'm going to modify the side on the right to make this a parallel function. So we're going to be doing a million elements. The first thing I need to do is instead of allocating X on the host, we're now going to do what's called CUDA-malloc managed. And this is the unified memory call to actually create a managed piece of memory. And we're still using the host pointer, the host pointer X. We're not having to do a device pointer as well like we used to have to. It's just one pointer. We do the same for Y. You notice we're calling this contrived function random floats, which just creates random float data. And we're just using this one pointer regardless of which device it's on. Now finally, we need to launch our kernel. So instead of calling SAXPY CPU, we're now going to call SAXPY GPU. And you'll see there's these new triple angle brackets or chevrons. Here we're simply telling the hardware how many blocks we want and then how many threads per block. So this is our way of telling the hardware how to do this. Coming up with these numbers is a different talk. Trying to optimize this just becomes one of the optimization steps you're doing. In this case, I just arbitrarily picked 256 and then made sure I had enough blocks to cover the amount of data I had. And that's it. So that actually launched on the GPU. We'll wait for this is a synchronous call from an asynchronous call from the host perspective. And then finally, we would clean up. So when we're actually done, we would just use CUDA free instead of free. So that's all that was required to actually call this actual CUDA-enabled language. And again, you would only go to this level of actually writing GPU code if the other levels above you, libraries and directives either didn't get you what you need or you wanted to get in and actually optimize as much as you could. Just on to tools we have available. So what we call Nsight. So we have the Eclipse edition for Linux and Mac. This is a fully functional IDE that plugs into Eclipse. Gives you source line debugging of GPU code. You can set break pointers where it stops, just like you would on the CPU where it stops. You can, single line step through. It has great debuggers, so you can go in there and look at an individual thread to see its thread counts. It's got a nice visual profiler, so you actually see a timeline of what's happening. Parallel programming is inherently more complicated than serial programming. This is a really great visual way to get in there and debug and optimize your code. And we have the same thing on Windows for Visual Studio, which also works for the Express edition. And then we also have our visual profiler, which we put a lot of work into recently. And this is actually will run your code and give you human-readable guided analysis on how to best improve your code. And this works on OpenACC compiled things, since it's just working with hardware counters. You can actually go through and see a timeline, click on an individual kernel launch to see what's happening, go through the guided analysis. It'll give you, source hot spots where it thinks you can improve. It's a really great tool that a lot of effort's gotten into it. Because, the whole point of going to parallel, to going to an accelerator, is to get your code to run faster. And so if you're not using a profiler to do profiler-led optimization, you're really doing yourself a disservice. So that's kind of the technical part, actually doing some GPU programming. I only have 50 minutes here, so I'm going through that part kind of fast. I'm going to get back into more just some examples of where accelerators are being used, outside of the traditional space you would think. And one of the big buzzwords today is big data. Not just doing molecular kind of simulations in a supercomputer, but processing big amounts of data. And here's some examples of what's being done today. Analyzing Twitter. Twitter gets some crazy number of tweets every day. It's like 500 million, or I don't remember off the top of my head. And Salesforce is one of, I think, of 6 companies that gets full access to the Twitter fire hose, so they get to see every tweet coming in. And they would like, for their customers, they want to do real-time searches. Somebody puts in a search, they want a real-time search of all these tweets and then being able to process data over time. And before moving to accelerators, they were having to wait. It was not real-time. It was starting at 10 minutes and then growing and growing as the number of tweets grew. And it was just this unsolvable problem until they went to the heterogeneous computing by using accelerators to process this massive amount of data. And so now they can actually do real-time search results by using accelerators in a big cluster of systems. And so it's processing all this data. So it's not doing all these very complex algorithms, but just doing it on terabytes and terabytes of data. Shazam, if you've ever used Shazam, which is just a cool little app. If you are listening to a song and you want to know what it is, you hit a button on Shazam, and within a few seconds, it's like, oh, it's this song. So they're actually using accelerators as well to do all this processing. They're quickly growing in the number of people using this service. They've now moved into being able to do this for TV commercials and others if you want to see what the product is or what's going on. You can search it, and by moving to accelerators and spreading this work among the thousands of processors available, they've been able to drastically speed up the time it takes to return a result. Visual shopping, so Cortexica and eBay, they're doing things such as you see a cool pattern on a couch. You can take a picture of it, and again, within seconds, you get a search back or the results returned that will show you all the things that are similar to that pattern. Whether it's a shirt, other couches, dresses, whatever it is, it'll say, okay, this is all the stuff that's very similar. And this is, again, just a massive data problem. You have all this data, and you need to do comparisons again. And, stuff like real-time video, very similar. A lot of like what you saw at the Olympics or the Super Bowl was done by, embedded over time, overlaying it with these graphics that come into it. Or if you want to stream video to lots of different devices where you have lots of different types of resolution, instead of trying to compute all those different resolutions and store all that data, you can now just do it real-time processing of the video to all the different resolutions available. So big data is becoming a very interesting area for accelerators, beyond the traditional HPC space. One of my favorite examples, this is a really old example. I know it's by Intellectual Ventures, which people aren't a big fan of, but I really like this example. I apologize, this is a black window here. This is normally a video. This is a project to fight malaria in third world countries. This is, again, an old project which has kind of died off, but I think we're going to see a resurgence of it, which I'll talk about shortly. But traditional malaria fighting techniques was the mosquito net. It's the best defense they found in third world countries. And so what this project did was to set up a fence around, say, a hospital or a school or village. And then in each wooden post that they would have around here, they would have a small webcam and then a very low-powered laser grid going between each post. So that way, when something broke that plane, they could detect, A, that it happened by the break in the laser, and then using the webcam, they could detect that it was, not a dog, a bird, a kid, but actually that it was a mosquito, and then it was actually a female mosquito because they're slightly bigger and they have faster wing beats, and they're the only ones who bite, and so they're the ones who spread malaria. So they could do this with just an off-the-shelf camera, and they're doing the image processing with NVIDIA GPUs. And at the time when this project was going on, they were using our original G80, our original CUDA-capable GPU. And then once they detected that it was a mosquito, they would use a more powerful laser, which was actually a Blu-ray laser, another off-the-shelf component, and they would shoot down the mosquito in real time. So they'd hit it with a laser burst, and it actually, it kills them instantaneously. But if you go onto YouTube and just search for mosquito laser, they have slow motion videos of it happening. It's a really cool project. There's a TED Talk on this where on stage they're actually tracking mosquitoes from about 15 feet away with a little green laser. A really cool project, one of my favorite uses of a GPU. People traditionally think high-performance computing, big supercomputer, but this was a totally different use where they were, power efficiency and perf efficiency were really important, and so they went to the accelerator for doing, this massively parallel stuff that's important. So with our recent announcement of our Tegra K1 processor, which is taking the GPU that's actually in the Titan supercomputer, America's fastest supercomputer, and moving it down to something that's on a small system on a chip, something that's going to be in cell phones. I think we're going to see a lot more of these types of projects coming out. You have this massively parallel accelerator on just this very small, low-powered device, and I think the research area in this is going to be very big, and what people can do with all this power in a very small device. And we're already seeing it in cars, doing image recognition and driver assistance, and so this is going to be a very big area, I believe, going forward. You can think of Raspberry Pis if you've ever done anything with that small, self-contained system. Imagine that with all the full acceleration on it. There's the projects out there are pretty much endless and be very cool going forward. All right, so that's just some examples. I'm going to jump into the resources now. The one link, if you can't remember any others, if you're interested in the NVIDIA technology, is developer.nvidia.com/CUDAZone. I highly encourage you to subscribe to the Parallel for All blog that's put on by Mark Harris, our chief technologist for GPU computing. Lots of great posts, a lot more technical details if you want to learn about our new CUDA-6 stuff or the new Maxwell architecture we just launched, anything. I really suggest you subscribe to this blog. I also put on a series called CUDA-casts, which are short 5 to 8 minute screencasts actually showing how these technologies work, how to write code, how to translate it to CUDA, how to implement directives. If you're more of a learner that likes to watch what's happening, you can find these CUDA-casts on the Parallel for All blog. We've also created a number of these self-paced labs. One of my goals as CUDA educators to make sure that the lack of a GPU doesn't hinder massively parallel programming education. So these self-paced labs are one of those approaches. So this is the 90-minute lab. All you need is a supported web browser. You don't need a GPU in your system. It's all done through an Amazon-hosted GPU instance in the cloud. You go on there, you actually get to write code, edit code, run it, see how it's happening. And pretty soon we're actually going to have visual profilers built into the system. So it's a really cool way to quickly go in and try the GPU computing. All our documentation, docs.nvidia.com, for any of our tools, our libraries, the runtime API, whatever it is, that's your source for the documentation. And then finally, questions. Once you get started, where do you go to ask questions? So the NVIDIA Developer Forum is the first spot, devtalk.nvidia.com. We have lots of NVIDIA engineers watching this all the time. It's a great place to go have discussions. For more just like purely programmable technical questions, Stack Overflow is becoming the place to go for everything. So you go there and look for the CUDA tag. There's already something like, I think we're up to 4,000 questions that have been answered on CUDA. So most likely if you're just starting out, if you have a question, it's probably already been answered, so go search Stack Overflow. And if it hasn't, feel free to post there. Again, we have lots of engineers who are watching that forum and helping to answer questions. We have what's called our CUDA Register Developer Program. This is a way for you to tell us what you're working on. You register with us and say, hey, I'm doing GPU computing, whether you're actually actively writing CUDA or whatever it is, you're doing some sort of accelerated computing. It allows us to communicate back to you. We try not to make this a spam system, but say you're working on molecular dynamics, we can say, hey, there's this cool webinar coming up on molecular dynamics you may be interested in. We'll send you that. New releases of CUDA come out, we'll send you information on that. You get early access to software if you want to try it out early. You actually get to submit bugs directly to our engineering team and feature requests. And so it's a really great programming, and we try not to make this a spam bot. Try to keep it down on only things that we find interesting to you as a developer. So highly encourage you to register if you're interested in GPU computing. If you wanted to actually try out, one of those 270 applications I had, or your own application on a big cluster with our latest and greatest GPUs, you can go to our GPU test drive. If you sign up, you get SSH access in, and you get to run your code and see what kind of speed you can get, all without having to invest any money in the actual hardware. So it's a great way to actually test drive this. We have these all over the world through lots of different of our vendors, so it's a quick way to try out your code. We have our GPU Technology Conference. This is a big conference we do every year. It's growing and growing leaps and bounds every year, so this is coming up end of March very soon here. Covers the gambit from tools and actual CUDA stuff to what research people are doing with GPUs and accelerated computing, all the way from the HPC space down to the car infotainment and driver assistance to actual game development. So it's a conference dedicated to GPU computing, not necessarily graphics, but on the computing side. 500 plus sessions. I think we had 300 last year, so it's a really big conference in this area. If you can't make it, and we do provide you this for everybody watching this webinar, this 20% discount. If you can't make it, we record the vast majority of these that we're allowed to, the presenters allow us, and put them online at the same link, so nvidia.com/DTC. You can see recordings from all our past conferences we attended, Supercomputing, International Supercomputing, all the old GCCs. So if you're interested in an area of research or technology, you can go just search through that and see old talks. So, that's up there for free. We'll be putting the new GTC 2014s up there shortly after the conference. So if you can't make it, even though we encourage you to do it, you can watch it afterwards. And another benefit of actually attending this is we're going to have something like 6,000 man-hours of hands-on training, including hopefully our new on the Tegra K1, so you actually get on to actually be able to program this new low-powered supercomputer on the chip. And so lots of hands-on training that will be available at the conference. So if you're in San Jose and you can make it, I highly encourage you to attend the conference. So that was a lot of resources. You can download these slides and look through them. If I were just to give you the 5 steps for getting started with GPU computing, go to this link right here, the CUDA Education and Training. Try out GPU computing. There's different how-tos on getting started. Subscribe to the Parallel for All blog so you can see as new stuff comes out. Sign up as a registered developer to get access to all the new features, and so we can help you with your projects. If you have access to an NVIDIA GPU, install the CUDA toolkit. Lots of great examples you can work through and actually get started programming, or use the OpenACC compilers. And then finally, attend GTC 2014 or watch it on demand. All right, 11:49. I think we nailed it just on time. So I think it's time to open it up for questions. Jeff?
Thanks, Mark. Can you hear me?
Yep, I can hear you good.
Great. So we have a bunch of questions here. The first one is, could you sort of explain how GPUs are similar or different than both array processors and vector processing from days of old?
Yeah, it's actually a question. We were having this conversation right before the webinar. GPUs are very similar to the vector processor supercomputers of old. Like we kind of consider those the grandparents of the modern GPU. These are the supercomputers back in the late 80s, that were really starting to take off. But the problem with them is they were incredibly expensive and kind of one-off machines. So really only the priesthood of researchers got access to them. And then through economies of scale, Intel came in and people found they could build off-the-shelf white clusters in their closet, and while they weren't as powerful, they were much more dollar efficient. So the vector machines kind of disappeared for a while. So you could say the era of serial computing was kind of was the fad. We're getting right back to that parallel vector processing type of programming. So it's very similar. Obviously, there's differences, lots of advancements, but if you find somebody who used to work on those old systems, they find that GPUs are very similar.
Great, thanks. So next question, we actually had a number of people ask in various forms, is how can you get at the benefits of GPUs if you're programming in other languages, in particular, I think languages such as Java, C# or Objective-C were popular questions.
So one of our approaches to this from NVIDIA's perspective is we open sourced our compiler chain using the LLVM compiler. And so this has allowed companies such as Continuum Analytics with CUDA-Python to get in there and actually target, either NVIDIA GPUs or different processors by using the LLVM tool chain. We couldn't implement all these languages ourselves. We don't have that bandwidth. So that's why we open sourced it. So there's a lot of languages being added, like F# was one. There's the C#. There's some various parallel programming languages there that we're looking at implementing. We're looking at the C++ 11 spec. So that's kind of our approach. A great research area as well to going in and looking at adding CUDA-enabled support to various languages through our open source compiler.
Right, and I guess the follow-up question someone asked was related, is it possible to call out to libraries from some of these other languages to things that are written either in the native CUDA or something else? So if you
most definitely. Before the CUDA-Python came along, like there was what's called PyCUDA, which is an example of this, where they were actually wrapping C, kernels you were written in C and calling it from Python. That was done long before the GPUs came along. So similar with MATLAB. MATLAB you can actually call a C kernel. So write it yourself, call it from a MATLAB. It's a great way to prototype. Just reminded me of the previous question. So Java is looking at adding just parallelism inherent in Java, and then so compilers could decide whether they wanted to target NVIDIA GPUs or AMD GPUs or Intel Xeon Phi. So Java is actually looking at adding this as well.
Great. So next question says, GPUs are great for lots of things, especially computation, and this person's asking, what are things that it might not be so great for, and in particular, what is the story if you have to do a lot of I/O from a GPU device or get a lot of data in and out of a GPU?
It's a good question, yeah. Data transfer or memory movement is really kind of, in computing in general, is where we spend the majority of our time and power from the macro level, getting it to a supercomputer or off a file disk to, the micro level, actually on chip. Data movement is where we're spending all our time and power, and that's really the big barrier to the exascale, getting exaflops. And so, yeah, that is something you have to be very cognizant of, is data movement, getting it to the GPU. So one of the ways that modern GPUs do this is they have, copy engines, multiple copy engines that can overlap communication and computation. So, you send over a little bit of data, you start processing it, and while that's happening, you're starting to send the next set of data, and so on. You kind of create this pipeline of transfer. And so it's a very important question. That's where you're going to spend a lot of your time optimizing, is data movement. So, GPUs are really good at the computation. There's a lot of work going into making this data movement more efficient, much higher bandwidth, more memory on the chip, being able to move a lot more of the computation to the GPU, so you just have to move that data once and just keep it over there. Our GPUs can now, through MPI, various MPI implementations, can directly talk to the network cards, so you're no longer having to go to system memory to send data, between nodes. So it's a very important area, and it's a good question. And so things GPUs aren't good at, they're not going to be great at file I/O. There's been some research projects on it, but that's just not what they do well. They're not good at algorithms that require lots of communication between the threads. Threads can't be independent. That's something that you'd leave on the CPU, making a few threads go really fast. But any kind of massively parallel program is what you want to target.
Great, thanks. So a number of people are excited about the unified memory features of CUDA 6.0, but a couple of people were asking questions about is there a performance penalty, or if I really want to be specific and say this memory is more for the GPU or this memory is more for the CPU, can I still do that?
Yep, definitely. So yeah, unified memory first and foremost is a productivity feature, especially in this initial release. It's being able to get the code on the GPU quick. And then, yeah, being able to manage the memory yourself is just an optimization that is available to you. So if it's not going as fast as you want, I mean, you know what your data best needed, you know, where it should be put so you can manage it. Just like with OpenACC Directives, I mean, you can have the compiler optimize your code and let it try to figure out your data, but you're most likely going to get better performance by getting in there and tweaking the data. And as with any compiler feature, you know, unified memory is going to get better performance over time. And its first release was really about productivity, and then we're going to really start tuning the use cases as we find them. You know, as our registered developers tell us where they're having slowdown, we can go in there and focus our performance improvements on.
Great. So, and I promise this is not my question since it's in my research area, but someone else asked it was, CUDA exposes lots of parameters that influence performance, things like block size, and what work is being done to develop auto-tuning or ways to help people automatically set these parameters in an appropriate way for their application?
Yeah, so that is ongoing research, both with NVIDIA and out, on how to auto-tune that. I mean, this is something OpenACC compilers are already doing. They're trying to do a lot of this work themselves. You know, instead of you saying how many blocks and threads, you know, the compiler's figuring out what it thinks is optimal. So that is an ongoing area of research, you know, both, like I said, internal NVIDIA and out, on how we can help with this developer productivity, not having to worry about those things. So, you know, there's research papers out there you can look at. There's, you know, stuff we're looking at within NVIDIA to help with this as well. So we are aware this is something we want to try to get rid of, or at least make not a requirement, you know, become just another optimization you can do. But yes, that's a good question.
Great. Another one we've had a couple people asking about is, could you explain the relationship and the role you see between FPGAs and GPUs in the space of, I guess, scientific computing ecosystem?
So yeah, so an FPGA are really targeted at, you take a specific algorithm. You know, Bitcoin is a great example of this. When Bitcoin mining first came out, GPUs were the hot commodity. We see this with the other versions of Bitcoin, the Litecoins coming out, where your best performance on these things were GPUs, and then people realized it's a very specific algorithm. I mean, you're just doing one thing, so you take that algorithm, you put it in FPGA, and it will run faster. So, I mean, Bitcoin's left GPUs long ago. They now run on FPGA-type machines, which is great. I mean, you get a lot of performance, but once you program that FPGA, it can only do that one thing. Whereas, you know, just same with CPUs. It's regardless of the processor. You can make a hardware that does one thing but go really, really fast. The great thing about GPUs and processors in general is their general purpose. You can change the code at will. You can do what you want. A good example of this would be like a soft modem in a cell phone. You know, traditionally, the modem was a piece of hardware that had a hard-coded algorithm. Now, if you move to a soft modem and you can get it to run fast enough, you can now change that algorithm at will. So say you're out in the middle of the Midwest where you have one cell tower within miles, you change the algorithm to operate differently to get a better signal. Or if you go to New York where you have hundreds of cell towers, you know, within a very small area, you can then change the software that's running on that soft modem to a different algorithm that runs better. Whereas if you force it to be a specific piece of hardware, you can't change it. So it's a balance. You get better perf, but you're locked into that one algorithm, and it's really hard to change.
Great, thanks. So another question that's come up on a couple forums is, you talked at the beginning about NVIDIA chips being available in various form factors, and you held out the example of the PCI Express, which I think most people are familiar with. But can you talk about what other form factors of fusing CPUs and GPUs that either NVIDIA has out or will soon have available?
Yeah, so for us, for NVIDIA, that's the Tegra K1. So we have our Tegra line of processors, which are system on a chips, traditionally targeted at phones and tablets, where you have your entire system is on one piece of die. So up till now, we've kind of had not the best GPUs, I'd call them, in our Tegra line, but with our Tegra K1 coming out, we now have our full desktop Kepler GPU in the system on a chip. So on a single piece of die, the same piece of silicon, we have this GPU in there. And so it's going to be fully CUDA capable. You can program it just like you would in the high-end GPU and the Titan supercomputer, same feature set. And so and all that power is going to be there available to you. And like I said, I think there's some really cool applications coming out. Now that you have all this input data, you have accelerometers and cameras and infrared and all this stuff that requires, they're massively parallel problems, interpreting those and doing something with them. So combining our, a low-powered CPU core with this high-powered but very power-efficient GPU, I think we're going to see lots of very cool projects coming out of these small form factors. So that's one of the form factors available.
Okay, great. and I think we have time for maybe one more quick question. And there was one talking about alternate level floating point precision. And so is there any plans with NVIDIA to support things other than IEEE single and double, in particular quarter precision or quad precision?
So nothing announced on our roadmap at this time. We're focused on, IEEE 754 single and double precision. As the needs come in, I mean, this is another great thing to become a registered developer. You tell us what you're working on. And if we see a need out there, we can definitely go invest. I mean, this is how we usually design most of our features and products, is what the industry and the world needs. So tell us about that stuff. We would love to learn so we can figure out if we do need to go after quad precision, if it's whether we can continue doing it as just a software, add-on with the compiler.
Great. So I'm afraid we're out of time today, so I would like to thank Mark for his informative presentation and insightful answers. And I also want to thank everyone for tuning in and taking time to participate today. We would like one last thing is we would encourage you to participate in the survey that is now on the screen. And also, if you'd like to come back and view the seminar later or see the additional materials, you can always come back to learning.acm.org/webinar. Thanks. This is Jeff Hollingsworth saying goodbye, and hope to see you in another webinar.
Hey, Jeff, real quick before we go, I forgot one thing.
Oh.
If people want to email me, you can send an email to CUDAhamster@nvidia.com. People seem to remember that after my talk for some reason. And I will be at the ACM 60 conference in Atlanta next week, so if you want to meet up, please send me an email, and we can meet up. Thanks.
Great. Thanks a lot. Thanks, everyone.